overfitting is a big no-no in data science, so we try to avoid it at all costs. So now I ask you to use a new data set, blood loneliness, so you can get it in the link here. This is a funny data set, actually. You can just enter the link here, press enter, and the data will be loaded. So it's very easy to load this data set. And this data set has, if we look at it, so it has 93 instances, and these are people. So these are like old people. And they were asked whether they feel lonely or not. So individuals that are lonely are here, and then we have some non-lonely people. Okay? So our target variable is to predict whether a person feels lonely or not lonely. And then we have almost 20,000 features with strange names, and these are actually genes. So they took blood samples from these people, and they recorded their gene expression in the blood. So the task here is to use the blood, whether loneliness is reflected in blood. So can we use blood samples to predict whether a person feels lonely or not? This is the task. And these are gene expressions that were taken from blood samples, and the target variable is feeling lonely or not. So it's simple classification. So here you have the first workflow and the second workflow. And here you have free answers, free questions. So use logistic regression and see how it performs on test and score. And then, so, you know, we have a huge data table, as you saw, like really big. So it would be nice to have just those genes that actually matter, not just random genes, but those that are actually important for the task, right? So your task is to select 20 best performing genes and use them for prediction and see what happens. Okay, so the assignment was the following. We had this blood loneliness data set with loneliness labels, so lonely, not lonely, and blood measurements, let's say, to simplify it. And I'm going to use logistic regression. You could use, any learner. I know that logistic regression should work quite well here. And then I look at the evaluation results, the scores in test and score. Are they good? Classification accuracy is 62%. It's like, so-so. I mean, it could be better, but it could be worse. So the one that's really important to look at here is AUC. Because you know that for a random classifier, so just randomly assigning labels, it should be 0.5. And this one is 0.3. Which means it's worse than random. So this is extremely bad, right? So worse than random, I mean, if you're ever below 0.5 on AUC, this is completely rubbish. You can just, draw the labels out of a bag, and this is it. Perhaps the model was bad because it has so many irrelevant features that I don't need, that confuse the model. There are so many, like 20,000. So let us just, keep the ones that actually matter and not, remove the rest. This will speed up the computation, and it will make the model more relevant to the task. So we can do this with rank. And I'm using rank to score my features, these strange gene expressions that I don't know how to interpret, but there's like some features. And let's say I take the top 20, right? Because I have 20,000, so I keep 20, not just 5. This is not enough. Maybe 20 is a good number, just to have some kind of sensible model. And then I look at the scores in test and score, same for logistic regression. And what do you think about these results? Much better, right? So classification accuracy is higher, it's 0.8. AUC is higher, it's almost 90. What does this mean? Essentially, the conclusion here would be that I can predict if a person is lonely based on its blood, on the person's blood. I mean, for me, this is really surprising. Do you think that loneliness is encoded in our blood? The title of this task was overfitting. Where do you think is overfitting here? So we are using cross-validation, right? So the estimate is quite okay. I mean, we are using 5 folds, and each time 1 fold is used for testing. And these are the scores that are reported with testing. So testing each data instance exactly once. So let us think about this step by step. So overfitting in general would result in models that are very good, so highly accurate, but accurate on the data that we already know. So here I'm seeing a very bad model. So it's hard to say that this is overfitting, especially because I'm using kind of like correct procedure, right? I'm using cross-validation, reporting the scores for the test data, and still my accuracy is unbelievably bad. We have like 93 instances, so 93 individuals, and 20,000 features that describe these 100 individuals. So this is what we would call wide data, because it's very, very wide in terms of columns, but it's very like short in terms of individuals that we measure. And in biology, this is quite common. So you would have just a few samples, but you would have gene expressions for many genes. So your premise is that it's very bad to have too many features. But is it not the case that more data is better? How do we know? Okay, I know that I have to measure these genes, but should I just 20, 21, which are really relevant? So this is a little trick that is not entirely intuitive, I will admit, but actually we're overfitting with rank. So we are saying, let's keep, 20 features most correlated with class. But this is tautology. So logistic regression, I mean, of course, the data set the model will perform well with features that are highly correlated with class. I mean, that is the nature of the model. The more correlated features I have, the better the model. So by selecting 20 best performing features, I'm overfitting the data because I'm already selecting the data based on the task that I want to do here. And especially with data like this, when we have many features, some features will be randomly correlated with class. So by chance. I mean, if I have 20,000 features, some will inevitably be correlated with class just by chance. And then I somehow conveniently select 20 best performing ones. So this will be another form of overfitting. if I select features that are correlated with class before building the model. Because I'm doing feature selection, so I'm using the knowledge about the class before I'm actually building the model. So the right answer here would be no, you cannot predict loneliness from blood. I mean, this is intentionally a very silly task, because when I first saw it, I was like, come on, you cannot predict loneliness from blood, from gene expressions. This is, I mean, come on. And then you see this high accuracy here, and you're like, what? Maybe you can. But the right answer is you cannot, because it's a very silly task. And what you have to do is actually like this. So feed entire data to the model, and then use feature selection. So I can still use feature selection. Okay, not random. So select relevant features. And I will use 20 best scored features. So the same thing basically as before, but I will pass it to the learner, so to the procedure that I'm sending here. And the difference is that cross-validation will use different 20 top performing features for each run of cross-validation. So for each estimation, for each test, for 5 folds. So 5 times a different subset of 20 features will be used. So because this is a big data set, things are quite slow. But we should expect a bad model again, because the task is not very, it's quite funny. The key takeout here is that overfitting can come in many shapes and sizes. And this is why data science is kind of hard, because you need to be careful not to overfit. And this is something that we try to really stress in our courses, all the ways that you can overfit the data. And this is clear why these things happen. And now it's finished, and we see that we're still below 0.5 with AUC. So it's still a very bad model with correct selection of features.